Hello everyone, welcome to the course on architectural design of ICs. So, we are discussing mainly the timing issues which we found mainly in digital IC design. So, till now we have discussed there are several problems which we have to consider to check the actual performance, what will be the actual performance of the chip whenever it works in the real time. So, we have to consider all, or we have to consider or constrain your clock with all the aspects of the original behavior of the clock, so that we can get actual performance of the circuit while we are doing the simulation. So, we can generate the divide by clock 2 very easily by connecting the clock bar pin to the input port of a single resistor, which will be a very easy circuit to divide or to generate one, that means divide by 2 clock. So, by that configuration actually we can generate very easily the by 2, by 4, by 6, by 8 in the power of 2 divide by the power of 2 clock generator very easily. Now, in some case we may find that we require divide by 3 clock. Okay. So, on that particular aspects, how we can define or how we can generate the clock 3 generator, not which is not in the power of 2. So, at that time what we can do is that, suppose we are having this system clock and divide by clock 3 means at that time we need two different these resistors, where this the output of the first one and the output from the second flip flop, they are basically connected with a particular AND gate. Okay. So, what is the meaning of this is that, so and the Q bar is basically connected to D. So, why it is divide by 3 whenever we are dividing by 3. So, at that time it is basically mainly this Q and Q bar. Okay. So, both if I say that okay, the primary thing is that we have for divide by 3 we need some terminal count consideration. Okay. So, so suppose this is the input system clock. So, whenever at this particular clock edge the Q is 0 and this Q bar is 1. Okay. So, at that particular time this is 1 and this is 0 means this is also 1. So, then it will this D input, that will be just 1. Okay. So, depending on that, now it will try to go up to this. So, whenever we find that okay, there is another edge. Okay. So, at this particular edge, so at that time what is this for at that time the output from this. So, earlier it was like the input from this is 1. So, at that time this will be 1 and then again this will be come down to 0. Okay. So, 0 means here at this particular edge. So, this will become 0. So, 0 will come over here and as this is 1. So, this will be also 0. So, after that means at this particular edge it will try to consider this up to this, and in this particular edge it will come down to 0. So, why it will come down to 0 is that because this particular gate has some delay. So, whenever this is coming after some times, so at that time at this particular edge it will not find immediately that okay, this particular that the output from this is 1. So, it will after some times it can check and it can get or it can extend up to this, and then you will get for this particular edge it will get the value as the here as 0, then again for 0 over here, then again it will come, and due to depending on this q, again it will come, and then it will be just like 1. So, as this for 1, 2 and 3, this is 1, and then again it is 0, and again 1, 2, 3 for 3 clock edge it is 1. So, that is why this particular circuit will act as a divide by 3 clock generator. Okay. So, the primary actually thing is that initially as both are 0, so it is starting with 1, then again as it is here it is going 1 means again it is 1. So, 1 and 1 it will start from 1. So, after that every clock edge it will just check the value, and up to third clock, that means this edge only it will find that okay. So, this corresponding D input is 1. So, it will be 0, then again 0 will come, this clock divider, this at this the output of Q, that will make 0 for that. Again as this is coming as 0. So, 0 again it will affect this. So, here if it is going 0, then again it will be just 1. So, whenever I will get 0 over here, so after one clock edge or after one clock cycles, again it will make as 1. So, that means this is delayed by this 1 is continuing for particularly 1 cycles. So, in this manner we can, or in this configuration we can make the divide by 3 clock generator. Now, suppose we have to design one divide by 5 clock generator. So, at that time what we have to do? So, there will be 3 registers at that time. So, divide by 5 means I need 3 registers, and the corresponding logic will be here as we consider this as, let us say that okay, 2 will be the terminal condition. So, whenever it counts this 2 over here, so at that time it will make the sequence to 0, then again 0, 1, 2 you count, and then again you just make that as 0, or instead of that if you just make one FSM kind of things. Okay. So, there will be this 0, 1, 2. So, if you develop from that excitation table you draw, and then if you come down to the logic of that, it will just become the corresponding circuit. Okay. For divide by 3, what you have to do? Again you have to up to 4 you have to count, that means 0, 1, 2, 3, 4. So, 4 of this edge will be counted. Whenever it finds that okay, the 4, that means the 4 of this particular clock cycles has been counted. So, again immediately it will be come down to 0. Then again after for 1 clock period it will be just 0, then again it will be going back to the 1. Okay. So, something like that you have to generate, or you can create this divide by 5, divide by 7, divide by 9, divide by 11, any of this particular circuit related to this kind of configuration. Okay. So, now how you can generate divide by 2 clocks based on 2 different edges. So, suppose you are having these system clocks, now you just pass this system clocks through one inverter, where this will be just, that means negative unit clock. So, now you just this negative unit clock directly you just pass it to this one of this flip flop and another with inverted clock. So, that means this will generate for this particular A flip flop, it will generate at the positive edge, it will generate the divider clock, and here it will generate at the negative edge sense, because here it is as it is already making as that means inverted. So, it will be just inverted, that means at the negative edge at that time it will be creates the corresponding divide by 2 clock. So, then again generate divide by 3 clock with shifted edge. So, how we can do is that now you are having this two registers, then again the same configuration, and where this particular this from this particular block's output you will get the divide by 3, and from the corresponding q bar output you will get divide by 3, and which is in this q bar you will get a shifted version of this particular which clock signals you will get from this shift register 1 or the flip flop 1. Okay. So, then the paths which are there in the generated clock phase network is that you will be having one combinational path, you will be having one sequential path, and in this clock signals will be just connected to these sequential elements through passing through some inverters or some buffers. So, this IO latency we have already said, we already have seen that. So, suppose this is my block, this is my design, and this is the external block which is connected to my design. So, this is the input delay, this is the amount of input delay to my design, and if my block is again connected with some other blocks. So, then what will be the amount of delay requirement from reaching from this particular output to the input of the other blocks. So, that is the amount of output delay which you have to consider while we are designing our circuit. So, then this what is the false path example is that suppose as we are having A, B, C, D and we are having this condition. So, depending on this condition, as there are, that means all the paths are basically connected from A to B or C to this, D B to this, D to this, but this particular path will be never activated. Depending on the logic, this particular path will be never activated, which will follow that A to this. So, that is why this path is named as, or this path is called as false path. Okay. So, then what is the example of multi-cycle path? Multi-cycle path is that suppose we are having some logic something like this, that means we are having logic, then flip flop, logic, then flip flop, logic, then flip flop. Then again here in this we are having some slow logic. Slow logic means suppose here in this all these are basically, let us say let us consider these are connected with full adders. Here inside of these two flip flops we are having one this memory cell, or sorry, one this multiplier cell or multiplier logic. So, the multiplier logic requirement, delay requirement will be much more than this full adder cell. So, which will basically though the requirement, timing requirement for this logic is much more smaller. So, depending on this this corresponding multiplier logic, the overall design cycle time will be much more reduced. So, that is why if you assign that okay, this particular logic require multi-cycle to complete the whole operation. So, at that time this path has to be considered as multi-cycle path. Okay. So, how we can in any of this example, how we can actually check in timing analysis tools, or actually using some mathematical modeling, how we can check what is the, that means setup time violation or setup time requirement, or what is that means hold time requirement. Suppose we are having some design configuration something like this. So, the setup timing check from this is the this flip flop 2, flip flop 2's clock pin to the flip flop 2's D pin will consider the maximum delay for clock path 1, this is the clock path 1, then the maximum delay for data path, this is the maximum delay for the data path, as well as the minimum delay for the clock path 2, as well as the minimum delay for the clock path 2. And the hold time checks for the, that means this DL2 to this, the input of this will consider the minimum delay for this clock path 1, then the minimum delay for data path 1 and the maximum delay for clock path 2. Okay. So, all this it will consider. So, depending on this, if I first let us check what is the setup value requirement for this particular case. So, the tools will check for the setup violation, or manually also I can check if I know all these values, delay information of all these values. So, at that time this the setup requirement is sets that it will check for the maximum delay for clock path 1, maximum delay for data path, and the minimum delay for clock path 2. So, the clock path 1, then the data path max minus clock path 2 plus setup less than should be the clock period. So, in this section, that means in this particular circuit, we are having this clock path 1 is this 0.8 plus 0.6, which is the summation of CT1 plus CT2, CT3. Then the data path max, which is this path, is 3.8. Then the clock path 2 is 0.8 plus 0.65, so 1.45, and the setup requirement for the flip flops is 0.2. So, the clock period must be at least this clock path 1 plus data path 1 minus this clock path 2 plus this setup, which is this 3.95. So, this will be the setup time requirement of this, or I can say that okay, the minimum clock period should be set for this will be 3.95 to meet the all constant in this particular circuit. Now, for the hold check, what will be the consideration for the same basically same circuit. So, not same, actually here the that means the parameters have changed. So, the configuration is same. Now, for hold, actually for hold, what we have to consider? The minimum delay for clock path 1, the minimum delay for the data path, and the maximum delay for the clock path 2. So, the equation is that clock path 1 plus data path mean minus clock path 2 minus hold. So, in this equation the clock path 1 is this 0.5 plus 0.3, which is 0.8. Then the data path is basically the minimum of the data path is 1.6, the maximum is 3.1, the minimum is 1.6, okay, 1.6. Then the clock path 2, this clock path 2 is 0.5 plus 0.35, which is 0.85, and hold requirement is 0.1. So, there will be no hold when as the corresponding equation 0.8 plus 1.6 minus 0.85 minus 1, this is 1.45, which is greater than 0. So, that is why this design will not consider any of the hold violations. Okay. So, now if you consider that means if you get this value as less than 0, so at that time you will find the hold violation. So, when you will get the hold violation means what? The data reaches too early. That means, if this particular value is let us say 0.1, so at that time you will get this value as minus 0.05. So, minus 0.05 means that much of hold violation you will get in this particular circuit. Okay. So, this on chip variation for worst case condition, then again this setup actually you can consider this clock path 1 here, actually on chip variation means you have to consider the minimum and the maximum both depending on the this process voltage temperature variation condition. Okay. So, here you are considering that okay, for worst case the delay is 0.8 plus 0.6, so 1.4, that is 100% of the worst case, and in worst case the data path delay is 3.8. So, here it is 3.8. For the clock path it is 0.8 plus 0.65, which is 1.16. Okay, sorry, not actually for this we are considering the minimum, okay, sorry, minimum delay we have to consider. So, here we have to consider the minimum delay for the clock path 2. So, minimum delay for the clock path 2 is this 0.52. So, 0.52 plus 0.64, that is 1.16, and setup is 0.2. So, the minimum clock period requirement at least will be 1.4 plus 3.8 minus 1.16 plus, so 4.24, which will be of this same case. So, in this particular case we are considering only single case, but in this case we are considering as well as best case as well as worst case. That means, if particularly this information, this delay information is already given to me, then only I can say or I can use them to calculate what will be the time requirement for setup or hold in any of this circuit. Okay. And here actually manually only you can do, as you are having only 2 resistors and you are having only 1 or 2 paths. So, that is why it is much more easier. But whenever you will work on this complex circuit design, so at that time you might find that there will be millions of paths which consist something like this configuration. So, at that time each of these paths you have to calculate. So, each of this calculation manually it is not impossible to do, it is not possible to do. So, that is why at that time what you have to do, you have to, based on this equation, the EDA tool or this electronic design automation tool, they calculates and it shows that okay, you are getting each of the paths, they calculate and it shows that okay, you are having this much of paths. So, among them if there is any violation, so which path are getting with how many violation, then that will be shown to you. If you are not getting any violation, so at that time with how much slack you are getting, what is the results with the slack, that will be indicated in the timing summary report of the whatever tool you are using as the static timing analysis of your circuit. So, here manually you can actually, this is just as an example that how you can calculate the each of these paths, that means the timing analysis value. Now, if you are suppose from the circuits aspects, suppose you run that tool for timing analysis and then you see that okay, for some paths you are getting the result, that means you are getting some of the violation. So, at that time you can identify that path and then again you calculate manually that okay, this is the information about the delay. Now, what changes should I make so that I can overcome the problems of this violation and my chips work perfectly fine. Okay. So, for that reason you have to know how you have to, or what particular aspects you have to calculate for hold check as well as the timing check while you are doing the timing analysis. So, now how to calculate this, or how this tools basically calculates the corresponding this net delays is that, suppose this is one, U1 U2 is one of the block, U3 is another block. Now, they are basically connected with this. So, these are the nets. Now, all this is connected like this well load model. This is a well load model of U2, this is the well load model of this particular nets. So, which corresponds to some of this capacitance value as well as this resistance value, then again this resistance value. Now, again it is connected with this another well load model which is going to this block U1 and then it is going to the well load model of block U3. Now, based on this, now the SPICE simulation will run in the background and it calculates that okay, for this configuration or for this capacitance and resistance value of this, what will be the corresponding delay for this particular path. It calculates and depending on the corresponding loads, this value changes, the capacitive load changes. So, depending on the calculation, the value will be reflected on the timing analysis report. Then this is the actually how we in physical design, this is the that means steps which is followed for the timing analysis. You are having the RTL. So, then initially this we have to set the RTL load, then you compile, you do the place and route and then you read the corresponding standard delay format SDF file, and then calculate the RTL load, write the RTL load, and then again extract the RTL load values. Extracted means all this C and R, depending on the well load model you have chosen. So, all the C and R values you have to extract, and then again it will be back annotated and it will be calculated depending on the whatever RTL code you have written. So, it checks the timing. You have, suppose you have set the timing, okay, my clock period requirement is let us say 5 nanoseconds. So, it checks, it performs all these steps, and then again all the delay information is calculated, and then again it corresponds to your that your required time. So, you are, if you have said that is 5 nanoseconds, so that is your required time. Now, the actual time will be calculated based on this particular loop. So, actual time, if it is more than 5, so at that time you will get negative slack. If this particular this path corresponds to the lesser value than the required time, so you will get positive slack. Okay. So, this is okay. So, actually I was saying that, okay, in clock gating you will get, sometimes you will get the glitch. So, if I say that, okay, this is the clock 1 and this is the second flip flop is basically getting the clock gated one, which is the clock 2 signals. So, clock 1, now the gate signal, if it is something like this, so at that time then the clock 2 will be here, as this is 1, this is 1. So, it will be 1, but because of this delay in the clock 1 and the gate, you will get some of the glitch over here. Okay. So, when you will not get the, actually the glitch over here is that if the gate signal is something like this, at that time there is no such glitch at the clock 2, and in the actually here, if you are getting any glitch, means what, the corresponding circuit performance will be totally wrong. Okay. So, that means if you are having glitch is the unwanted signal which we got in our desired signal. So, whenever it finds 1, so at that time the corresponding data, unwanted data will be sampled in the second flip flop. Okay. So, that is why whenever we are doing this gated clock circuit design, at that time we must have to be very much careful about, so that this glitch may not occur at the circuit. Okay. So, then again actually we can get some of the, that means this is some of the configuration where we can get, because of the hold time, we can get the glitch at the clock 2, and that can create a problem in your circuit. So, this is this clock tree synthesis. So, that means this is the clock source pin, then it is connected as H tree. Okay. So, you see from one buffer, then again it is connected with 2 buffers, then again 2, then again it is distributed to 2, and again by this will create the network, and it will connected each and every sequential element which are present in your particular circuit. Okay. So, then this particular circuit will be extracted through the SPICE simulator, and it will try to optimize, because here we are using that means in the that means as this is 1, then from 1 it is connected with 2, then 1, then again it is connected with 2. So, it creates this particular type of mesh for the clock network. Now, as these all of these requires the buffers, so we have to minimize the number of buffers. How we can minimize? So, through the SPICE simulation, it tries to minimize the number of buffers which is used for this particular cells, and it comes down to a lower number of buffers which will be used for the reduced clock network. Okay. So, in actually CMOS IC design, we are having different kind of source of power dissipation. So, you will be having this dynamic switching power consumption, you will be having this short circuit current power consumption, you will be having this leakage current power consumption. So, all these are there. So, if you are working on this low power actually digital VLSI design, so at that time you have to consider your design aspects in such a way, so that the power consumption in all these aspects should be in the lower domain. Okay. So, for this is this is it for actually this timing issues or the timing information. Okay. Next we will see that optimization, what we can do the optimization in the circuit, so that we can get the circuit performance in the higher side in terms of speed, power and area. So, thank you for today.